Hello everyone, Saulo Castro here. Welcome to our third video in the Rigid Body Kinematics series. In today's video, we'll go through another technique to calculate the velocities and angular velocities of rigid bodies undergoing general planar motion. This technique is called the instantaneous center of zero velocity, or just IC. I will refer to the instantaneous center of zero velocity as just IC throughout this video. In the previous video, we used the relative velocity equation to calculate the velocity at any point B based on the velocity at another reference point A. We also learned the meaning of the relative velocity VB/A, which represents the rotation of point B about the reference point A. This calculation procedure required the use of vector product, and it proved to be a powerful method. Today, we'll make use of another method called the instantaneous center of zero velocity. This method takes the advantage of the fact that for rigid body undergoing planar motion, there is always a point in the plane of motion at which the velocity is instantaneously zero. Note that the point lies on the plane of motion, not necessarily on the rigid body. In fact, in the majority of cases, the instantaneous center of zero velocity, or just IC, lies outside the rigid body. We'll learn in this video that if the location of the IC can be determined, the rigid body appears to be rotating about this point, and therefore the velocity analysis, meaning the calculation of velocities and angular velocities, can be greatly simplified. In this first example, we can see that as the board slides down the wall, the IC stays always at the location indicated. And we can consider that the board is rotating about this moving point at any instant. After defining a coordinate system, we can relate the angular velocity of the board with the linear velocities at any point in a very straightforward manner. Note how the right-hand rule can be used to determine the directions of vectors VA and VB, such that only the magnitudes need to be calculated. For a bicycle wheel, or any wheel rolling without slipping, the IC is located at the point in contact with the ground. With this technique, using the position of the IC, note how simple it is to calculate the velocity of the wheel at any point, just multiplying the angular velocity and the magnitude of the relative position. I want now to practice together with you different possibilities. For each possibility, different kinematic variables are given. And in all cases, what we want is to locate the instantaneous center of zero velocity. In this first possibility, we know the velocity at one point, denominated point A, and we know the angular velocity of the rigid body. Since the rigid body is rotating about the IC, we know that the velocity vector at any point must be perpendicular to the relative distance about the IC. So we already know that the IC must be located along this dashed line. The distance of the IC about point A can be easily calculated using the magnitude of the velocity vector at point A and using the magnitude of the angular velocity. And now, how to determine the correct side of the IC? For that, we need the right-hand rule, remembering the vector product that defines the velocity vector. Considering all these factors, there is just one possibility for the location of the IC. Now going to a second possibility, when we know the velocity at 2 points, but we don't know the angular velocity. Again, given that the velocity vectors must be all perpendicular to the relative distance of each point to the IC, we just use two perpendicular lines, and where they cross, we have the location of the IC. Note in this example how the rigid body rotates about the IC. In this third possibility, note that VA and VB are known, as in the second case. But now there is a difference that the two velocity vectors are parallel. So how to calculate the position of the IC in this case? We know that the IC must be perpendicular to the two velocity vectors simultaneously, because the rigid body is rotating about the IC. So we know that the IC will be located somewhere along this dashed line. However, how to determine its exact location? For this example, the velocity field along the rigid body must look like this. Looking at this velocity field and recalling that at the IC the velocity is instantaneously zero, the location of the IC can be visually determined. Note, however, that this visual determination would only work if vectors VA and VB would be drawn with their length proportional to their magnitude. And we know that this is not usually the case. A more robust approach is to use the relative position vectors RA/IC and RB/IC, both shown here. As we know, the magnitude of VA and VB can be calculated as given. This can be rearranged in the equation that I just showed. Note, however, that we don't know the magnitudes of the relative position vectors, but we know their sum given by the variable d. Now, if we plug this into the previous equation, we can come up with this equation for the RA/IC. So now we know the exact location of the IC for this case. Now I want you to pause the video and make sure you're able to get to the same equation. What would happen here if the magnitude of VB tends to 0? And what would happen if the magnitude of VA tends to 0? Think about it. Another situation of the two velocity vectors VA and VB parallel is when they point to the same direction. In the previous case, they were pointing to opposite directions. When they point to the same direction, by visual inspection, we know that the IC should be somewhere above point A, as shown here. The procedure that we used in the previous situation can also be used here, with the difference that the distance variable now represents a subtraction, leading to the following equation for the location of the IC. Again, make sure you pause the video to have some quick fun with algebra while keeping your skills sharp. What would happen with the position of the IC if the velocity VA tends to 0, or if the velocity VB tends to 0? Think about it. The fourth possibility that we will discuss in this video is a special case of the third possibility, when velocities VA and VB have the same direction and the same magnitude. Looking at the equation that we just derived, where is the IC located when the two velocities are the same? In order to answer this, think what happens with the angular velocity of the rigid body in this case. This fourth scenario is actually when the rigid body is undergoing a pure planar translation, and in this case, the IC is located at plus minus infinity. Going now for a quick recap. In this video we learned a convenient property of rigid bodies undergoing general planar motion. And this property consists of an instantaneous center of zero velocity. We learned how to calculate the position of the IC for 4 different possibilities. With this new resource, we can calculate more efficiently the angular and linear velocities on rigid bodies undergoing general planar motion. And this will certainly make our problem solving much faster. I hope you could learn already by watching this video. The intention, however, is that the video only triggers your curiosity to read the textbook material and start solving the recommended problems. Do this right away to have those concepts well consolidated. Don't hesitate to ask questions, and goodbye for now, and I see you in the next video or in the next lecture.